electricity. So today, let me just give you a quick overview of what we looked at last time. Okay, so some of the key points that we looked at when dealing with atomic structure in the periodicity is that all light waves have three primary characteristics. So all electromagnetic radiations, they do have three primary characteristics, and the primary characteristics is that they all have frequency. Now, frequency is just defined as the number of cycles per second. The number of cycles that pass through a given medium per second is known as frequency. So now it is denoted by lowercase Greek letter nu. So frequency is given by the constant speed of light divided by the wavelength, which is denoted by lambda. Now, keeping in mind to say where this one is just the frequency. So frequency is the number of cycles that pass through a given medium per second. Now the units of frequency is just hertz, which is just equivalent to a per second. So these are the units of frequency. And then the c is the constant speed of light. So c is just the speed of light. So the speed of light, the constant speed of light, is a value that is equivalent to 2.9979 times 10 to the power 8 meters per second. Okay, so the last character here, which is wavelength. So wavelength is just defined as, that's where you get this entire expression. So the constant speed of light divided by the wavelength, everything multiplied by what? Planck's constant. So in this case, h is Planck's constant, named after the German physicist Max Planck. So Planck's constant is a value that is equivalent to 6.626 exponent negative 34. The units is joules seconds. Okay, so that's the value for the Planck's constant. Everything you already have, like you have the constant speed of light. This is the constant speed of light. And then we do have the wavelength, whose units are supposed to be in meters. Okay, so the third stuff that we did talk about was the Bohr model. So number 3, the Bohr model. So the Bohr model is sometimes referred to as the quantum mechanical model for the hydrogen atom. So the quantum mechanical model this model, in 1921, a Danish physicist by the name of Niels Bohr postulated to say an electron in the hydrogen atom is found orbiting around the nucleus in only certain allowed circular orbits. So what do they mean? This model is only restricted to the hydrogen atom. My guess is because hydrogen has got one electron. It's the only element on the periodic table having one electron. So back in high school, if you do remember, we used to do our electron configuration in shells. So if this is our nucleus, the central part of an atom, you find electrons circulating around the nucleus in these certain circular allowed orbits. Now these orbits, back in high school, we used to call them shells. Well, the terminology is interchangeably with an orbital, so they are also called orbitals. The shells can also be called the principal quantum level or the energy levels. So now, he devised a formula to calculate the energy that is gained or lost by an electron as it moves from one energy level to the next. So an electron can move, so these are energy levels denoted by n. So the first energy level is just n is equals to 1. The second energy level is n is equals to 2. The third n is equals to 3. It goes up to n is equals to infinity, like that. So an electron is capable of moving in between these energy levels. So now the energy that is gained or lost by an electron as it moves from one energy level to another can be calculated using this formula. A change in energy is equals to negative 2.178 times 10 to the power negative 18. You open parentheses 1 over n squared final minus 1 over n squared initial. Of course, you are going to use this formula if you've noticed to say, if the question requests to say, can you calculate the energy that is gained or lost by an electron, which is moving from maybe for example, n is equals to 2 to n is equals to 4, like that. So we did a series of examples in the previous session, the one that we had. Okay, so now today, our main focus, I want us to focus on quantum numbers. Okay, so these are 3 steps that we looked at last time, and we did a series of examples from the theory sheet. So for today, let's draw our attention to another subtopic of atomic structure, which is quantum numbers. So our main focus for today is quantum numbers. Okay, so if you want to try out, anybody can try out and explain to us what quantum numbers are. Okay, so quantum numbers can simply be defined as values that describes various properties of atomic orbitals. So these are just values that describes various properties of atomic orbitals. They are called quantum numbers. So values that describes so quantum numbers, these are just values that describes various properties Okay, so some of you might be wondering to say, what are these atomic orbitals? So an orbital is just a region in space where you do have a high probability of finding an electron. So an orbital is just a region in space where you find electrons. So now by convention, we do not to say electrons are found arranged around the nucleus called what? Shells. Now I told you to say shells can be used interchangeably with what? With orbitals. So now an orbital is sometimes referred to as energy levels. So an orbital is just a region in space. So any region in space where there is high probability of finding an electron, so an orbital is just a region in space where you have a high probability of finding an electron. Now, what you need to know about these quantum numbers is that we basically or essentially have 4 quantum numbers. So the first 3 quantum numbers, they just describes, the first 3 quantum numbers, they specify the size, the shape, and the orientation of an orbital in space. Now, the last quantum number, in other books, the last quantum number describes or specifies the maximum number of electrons an orbital can accommodate. Or in other books, the last quantum number, it only describes the spin of an electron. Now, an electron can spin in 2 possible directions. It can either spin in clockwise direction or counterclockwise direction. Or if you want, it can spin upwards or downwards like that. So there are 4 quantum numbers. The first 3 quantum numbers, number 1, it specifies the size, the shape, and the orientation of the orbital. And the last quantum number only specifies the number of electrons an orbital can accommodate. So there are essentially 4 quantum numbers. So the first 3 quantum numbers, they only specify the size. So the quantum number that specifies the size, it's denoted by n. And the quantum number that specifies the shape is denoted by L. And then the quantum number that specifies the arrangement of an orbital, that is the orientation, it's denoted by ML. And the final quantum number, it specifies the spin of an electron. Okay, so we only have these 4 quantum numbers. So we're going to look at each and every quantum number one by one, and then we see, using an example, how both quantum numbers, how all the 4 quantum numbers relate. Okay, so we're going to start by looking at the first quantum number that specifies the size. Okay, so quantum numbers, they're just values that describes various properties of orbitals. An orbital is where you find electrons. So we have 4 quantum numbers. The first 3 specifies size, shape, and orientation. And the final one only specifies the spin of an electron. Okay, so now let's look at these quantum numbers one by one. Okay, so the first quantum number that we're going to look at is one that specifies the size. So the first one we have the principal, it's called the principal quantum number. So we've already established to say the principal quantum number specifies the size of an atomic orbital. Now, what you need to know about this quantum number is that it has values of n is equals to 1. It goes up to n is equals to what? To infinity. So it has all the positive integral values from 1 up to infinity. So the principal quantum number specifies the size So it specifies the size of an orbital. Now, keeping in mind to say an orbital is where you find electrons. So the principal quantum number has integral values of 1 up to infinity. Okay, so the principal quantum number has all the positive values from 1 up to n is equals to what? To infinity. So it has values, the principal quantum number can have values n is equals to 1. It can also have values, the principal quantum number can be n is equals to 2, n is equals to 3, 4, 5, going down up to what? Up to infinity. Okay, so now let's look at the next quantum number, and we look at one example, we see how the two can relate. Okay, so the first quantum number is a principal quantum number. It just specifies the size. It has values of 1 up to what? Up to infinity. Only those two essential information will be used for now. Okay, so let's check out the next quantum number. So the second quantum number is known as, of course, because it's a second quantum number, it's also known as the secondary quantum number. So quantum number 2. So secondary quantum number 2 is known as secondary, but if you want, you can use, it's also called the angular momentum. It's also referred to as the azimuthal. So the azimuthal quantum number. So it is just denoted by small letter L. So this is the second quantum number. It's called the angular momentum quantum number, or the azimuthal quantum number. What does it do? It only specifies the shape. So the azimuthal quantum number only describes the shape of an orbital. So now it has values. Okay, so this is the azimuthal quantum number. It has values of L is equals to 0, 1, 2, up to where the principal quantum number is less 1. So it has all the values from 0, 1, 2, up to n minus 1. So what do they mean by n minus 1? Okay, so what they mean is that if the principal quantum number, which is the first quantum number, if the principal quantum number is equal to 1, meaning the value of L will be 1 minus 1, which is just 0. So if the principal quantum number is equal to 4, L will have values of 0, 1, 2, up to 3, up to where the value of n is less 1. So if the principal quantum number is 4, L is going to have values of 0, 1, 2, 3, like that. So I guess you can now pick up the pattern, meaning if n is equals to 7, L will have values from 0, 1, 2, 3, 4, 5, up to 6, like that. Of course, the pattern goes like that. If n is equals to 100, meaning L will have values from 0 up to 99. Okay, now because the angular momentum quantum number specifies the shape of an orbital, for each value of L, there is a specific designation in terms of the shape. So for each value of L, if L has values of 0, 1, sorry, yeah, this is just an example, e.g., if L has values of 0, 1, 2, maybe up to 3, the designation or the specific shape, the shape or the designation for each and every value will be, so if L is equals to 0, the shape represented by the value 0 will be S. If L is equals to 1, the shape represented by the value 1 will be P. And then if L is equals to 2, the shape of the orbital will be a d orbital. And then if L is equals to 3, the shape of the orbital is going to be the F orbital, like that. So for each and every value of L, the specific shape will be S, P, D, F. Now what happens if we go to L is equals to 4? Of course, the shape now follows, it becomes G. If L is equals to 5, H. So you can follow the trends, you go down alphabetically. But for the sake of practice and the commonly encountered values, they run down from 0, 1 up to, most cases, up to 3. So we'll just leave our example up to 3. So for each and every value of L, there is a specific designation. So if L is equals to 0, the specific designation is S, P, D, and the F orbital. Now, of course, you do catch the trend. If we count the values of L up to 3, meaning the principal quantum number might have been something like 4. If n is equals to 4, meaning L will have values 0, 1, 2, up to 3. Now, the shape represented for each and every value of L will be S, P, D, and F, like that. Okay, so now let's talk about the sublevel designation. For instance, if the value of L has been given to be 4, or if the value of n, sorry, has been given to be 4, the value of L is going to be 0, 1, 2, up to n minus 1, which is 4 minus 1, which is just 3. Now, if we're to talk about the sublevel designation, so sublevel designation. Okay, so by sublevel designation, they mean to say for each and every value of n, there are sublevels or subatomic orbitals that can be designated or represented for each and every value of, for n is equals to what? To 4. For the principal quantum number is equals to 4. So the sublevel designation is, you just get the principal quantum number, or you combine the principal quantum number with the designated shape. So the sublevel designation just becomes the principal quantum number, which is 4. You combine it with the shape represented for the value of F. So it becomes 4s. Next, you have 4p. So the principal quantum number with the next shape in line, which is just becomes 4d. And the principal quantum number and the next shape in line becomes 4f. So this becomes our sublevel designation. Let me give you an example. So let's do one example. We see how questions do come on these, under these two quantum numbers. So example, Okay, so let's look at that example. For the principal quantum level, n is equal to 5. For the principal quantum level, n is equal to 5. Write down all the possible values of L and give the sub-level designation. For the principal quantum number, n is equal to 5. Write down all the possible values of L. So for the possible values of L, so L will have the values of 0 up to n minus 1. So it will be 0, 1, 2, 3, up to where n will be less 1, where the value of n will be less 1. So the values of L are going to be 0, 1, 2, 3, up to 4. Now for the sub-level designation, you need to keep in mind to say for each and every value of L, there's a specific shape that it represents. So the shape that 0 represents is S, P. If L is equal to 2, then the shape will be G. If L is equal to 3, then the shape will be F. If L is equal to 4, then the shape is going to be G. Therefore, the sub-level designation, you just combine the principal quantum number and the designated shape. So for the sub-level designation, it's just going to be the principal quantum number, which is 5, and the shape, which is S. The next 5, the shape is P. So we're going to have 5G, 5F, and 5G. So that becomes the designation for the sub-levels. Okay, so this is just a classic example on how the principal quantum number and also the angular momentum quantum number, they work hand in hand. Okay, so let's move on to the third principal quantum number, which is just the magnetic quantum number. Okay, so quantum number 3. So number 3. The third quantum number is just called the magnetic. So the magnetic quantum number is denoted by ML. The magnetic quantum number is denoted by ML. What does it represent? This one, we've already established to say it represents the orientation of an orbital in space. So the magnetic quantum number, this quantum number only specifies the arrangement, how an atomic orbital is going to be arranged in space. That is specified by the magnetic quantum number. So the values for the magnetic quantum number is that it has all the positive and negative values of L, including 0. So it has all the positive and negative values of L. So L in this case represents the angular momentum quantum number. So it has all the positive and negative values of L, including 0. So what do they mean in this case? So if, let me just give you a chart. So for the magnetic quantum number, it specifies the arrangement or the orientation of an orbital in space. It has all the negative and positive values of L, including 0. So meaning, for example, if L is close to 0, this side, of course we do not have something like a negative 0. If L is equal to 0, if L is close to 0, then ML will also be equal to what? To 0. But if L is close to 1, ML is going to have values of negative 1, 0, and positive 1. If L was equal to 3, for instance, then the value of ML will be equal to negative 3. So you start from the value of what? You start from the negative value of L. It becomes negative 3, negative 2, negative 1, 0, 1, 2, and 3. So the magnetic quantum number only represents all the positive values of L and the negative values of L, also including what? 0. So from these three quantum numbers, okay, so let's say, for example, for the principal quantum number, n, if n is close to 0, L, which is the angular momentum quantum number, it will have, n can never be 0. N has values from 1 up to infinity. So if n is close to 1, L will have values up to n minus 1. So if n is close to 1, L is going to be what? 0. And then, of course, we do know to say the magnetic quantum number represents all the positive and negative values of L, including 0. Now, because L is 0, so meaning ML can only be what? Can only be 0. Now, what happens if n is close to 2? Meaning L is going to have values of 0 and 1. Now, what happens with ML? So, if L is 0, meaning ML will also be going. ML is also going to be what? To be 0. Okay. So, if the principal quantum number is 2, L which is the angular momentum quantum number, is going to have values from 0, starting from 0, up to where 2 is less 1, meaning up to 1. So 0 and 1. Then what happens to the values of ML? So since the values of ML, they represent all the positive and negative values of L. So if L is 0, then if L is 0, then ML is going to also be what? 0. If L is 1, ML is going to be negative 1. Okay, so if L is equals to 1, ML is going to be negative 1, comma 0, and also positive 1. You do the same if N is equals to 3. So for the values of L, we're going to have 0, 1, and 2. So for each value of L, we're going to have the designated values of what? ML. So meaning if L is equals to 0, ML is going to be 0 also. We do the same, negative 1, comma 0, and positive 1. And if it's 2, if the value of L is 2, then ML is going to have all the positive values and the negative values, including 0 itself. So positive 1 and positive 2. Okay, so that's just some example. But of course, there is also the sub-level designation. So the sub-level designation. So for the sub-level designation, if N is equals to 1, L is equals to 0. 0, we do not say it represents an s orbital. So it's going to be, you combine the principal quantum number plus the designated shape. So the principal quantum number is 1. The shape represented by 0 is just s. You do the same if N is equals to 1 or if N is equals to 2. The values of L is 0 and 2. So for the shape, if N is equals to 2, L is equals to 0, the shape is going to be 2s. This time now N, L is equals to 1, sorry. L is equals to 1. For N is equals to 2, L will have values 0 and 1. So for 0, it's S, so the designation becomes 2S. For 1, it's P, the designation becomes 2P like that. You get the pattern. You're going to have 3S, 3P, and because we end up to 2, so we're going to have 3G like that. So these are the 3 quantum numbers that we've looked at. So this only specifies the size. So this one specifies the size. This one specifies the shape. And then this other one specifies, so the size, the shape, and this other one specifies the orientation. Okay, so those are their respective sub-level designation. For the final quantum number, it only specifies the spin of an electron. So the final one, just it's called the electron spin. So the electron spin quantum number Of course, from the terminology itself, the electron spin quantum number only describes or specifies the spin of an electron. Okay, so for the electron spin quantum number, this one specifies, so it is denoted by ms. This specifies the spin So the electron spin quantum number specifies the spin of an electron. So it has values of -half or positive half. Now, if remember that electrons can spin in any of these possible directions. Electrons can either spin clockwise or counterclockwise. So if the principal quantum number is designated by -half, meaning the spin of that electron is counterclockwise or rather downward. If an electron is denoted by the electron spin quantum number of +half, it only interpolates to say that particular electron spins in a clockwise direction, or if you want, you can just say upwards like that. So for each and every quantum number, for example, if you have a principal quantum number of 5, n is equals to 5, and then they've specified the spin of that electron in this principal quantum number n is equals to 5. So if this electrons have been specified by a spin of +half, it means the maximum number of electrons this principal quantum number is going to hold, because the principal quantum number specifies the size. So now the maximum number of electrons this principal quantum number of size 5 can hold is that the maximum number will be 50 electrons. So the maximum number will be 50 electrons. I'll show you how I got that in a moment. So the maximum number of electrons this particular quantum number will hold will be 50 electrons. Now, out of those 50 electrons, half of these 50 electrons, meaning 25 electrons, out of these 50 electrons, half of 50 is 25. So 25 electrons will be spinning clockwise. So if you've seen +half, meaning those electrons are spinning clockwise, or rather upwards. So half of those electrons will be spinning clockwise. Okay, so I'll show you how to calculate or determine the maximum number of electrons and the following principal quantum numbers can hold. Okay, so these are the 4 quantum numbers that describes the properties of atomic orbitals. So now, in summary, the first 3 quantum numbers, they specify the size, the shape, and also the orientation of an orbital. And the final quantum number, the electron spin, this one only specifies the spin of an electron or the number of electrons a particular orbital can accommodate. So for today's session, if there are no questions, if you do have questions, you can just leave your question in the comments below, or you can just inbox. We'll be able to assist. Thank you very much for your time.